Charlie and Anne-Marie, welcome. Thank you very much for joining us today. I will stop sharing my screen, and I think we're going to start with Charlie and then Anne-Marie afterwards. Cool.
Hello everyone. I hope you can hear me. And so I'm going to talk a little bit about embodied energy, the circular economy, and sort of building in general from what I know. And you know, I'd say it's one of these funny things that you think you're not an expert until you start talking more and more to other people in this sector, and you realize how new and novel it is, and how much we're all sort of working it out very much sort of almost from first principles. So this is just so what I know, and whether that's of help, hopefully you can tell me at the end of the chat. So you know we've got a massive problem. Buildings are responsible for a huge amount of carbon emissions, about 49%. And that's in a developed economy, but across the world, the figure's sort of up and down a bit, but it's pretty similar. I think that the mind-blowing statistic that I had recently, which was that over the next 40 years, the world is expected to build 230 billion square meters of new construction. So that is adding the equivalent of Paris to the planet every single week. Every week we're building something about the size of Paris, and you sort of, that's worrying. You know, the building construction industry is the world's largest consumer of raw materials. And we know that we've got to challenge something about that. And so we get these wonderful sort of, you know, Letty, who's a fantastic organization, and we have these plans about moving towards zero carbon. And I love this diagram because it's ambitious. I love this diagram because it feels very friendly. And then when you actually start driving into the reality of what you're trying to achieve, these figures are not little blue flags. They are systemic shifts to the entire way in which we not only design, build, and deconstruct, but for new buildings, it is also the way in which we then heat, obviously, and look at all the existing building stock. So it is a systemic change, although this diagram makes it look very, very pleasant. A big part of the issue we've got is to actually start thinking in a more circular way, and thinking really about the waste, because we're actually starting to tackle embodied energy quite well. But the issue is, as you make a building higher performance, the embodied energy becomes a significantly larger chunk of the overall carbon emissions that come from that building, because we're focusing much more on whole life carbon, so that's operational and embodied carbon. So I think it's fairly self-explanatory. Operational is the stuff used during the building, and the embodied is the stuff used to build the building. And critically, the embodied carbon is right from manufacture, transport, erection, use, refurbish, maintenance, deconstruction, and then disposal. So it is, as they say, the entire sort of piece. And I think this is a really useful diagram, again, from Letty, which makes you understand where the carbon associated with buildings come from. And so when you hear those 49% annual carbon emissions for the UK attributable to building, that is the full cycle, that is in use, actions within the buildings, and also the construction and end of life. But this kind of really sort of shows you the challenges that as designers and architects and engineers we are going to face. And the massive one is the embodied energy during construction. We know what we can do more and more about operational emissions, but there's still the replacement and maintenance cycle, and then obviously what we do with all the materials at the end. So really we need to start thinking in a much more circular way, and start to think about the full life cycle of our buildings when we're starting to design them. And so there's a kind of a number of things that I have tried to keep in mind, or try to keep in mind when we are working. And thing one is that the most sustainable building is the one that exists. And there's an American Institute of Architecture report that takes around 50 years for a building that is more than 30% efficient than the average to overcome the impacts of constructing it, right? So basically, we've only got a certain carbon budget left on the planet, and if we start knocking down old buildings in order to make them more sustainable, we don't have 50 years to make that all back, right? So we cannot be knocking them down. It's quite interesting that architects declare that, they're very clear that the impacts, from a conference a couple of years ago, it's very clear that really the most sustainable one is the one that you build. And no matter what metrics you seem to run, that seems to be the main message. So the first thing we need to look at is sort of systemically and intelligently refurbishing the existing building stock. So, you know, that's a kind of clear target, but what does that really mean? And actually, it's a clear target, not only abstractly, but actually in real terms, in that there's been a seminal or a very important planning decision recently where M&S were trying to knock down a large, or developers are trying to knock down the large M&S building on Oxford Street, and that was rejected because of the embodied energy in the existing structure. So planning is starting to catch up with this issue, probably quicker than most building owners. But how can we intelligently and systemically refurbish the existing housing stock? Well, there's a really good example is the Empire State Building. 102 stories, completed in the 1930s, 6,500 windows, okay? So it was in really poor condition. And over the last sort of decade, they refurbished the whole building. And what they did is on the 5th floor, they created a window factory. So they brought the windows down, they refurbished them through this linear process, and they took them back up and put them back on the building. So they coated and filled the glass, and they dealt with gaps and so on. The upgrade was $15.5 million less than the estimated for new windows, and they reckon it will save 100,000 tons of carbon over 15 years. So, you know, it's about intelligent, smart reuse, and this is something we've been trying to work on, you know, here, and we're working on a window solution, which is at the moment with all these secondary, well, poor quality double glazed units and single glazed units, we're taking them out and throwing in the bin. And a few years ago, I looked at this problem with my brother and said, this is ridiculous. You know, these single glazed windows, well restored and maintained, can last 50 years. Why aren't we looking at how we can make secondary double glazing that goes inside existing windows? Because we know windows are probably the most carbon intensive part of any building. And that's what's really interesting is when you go to Finland, they've had triple glazing for years, but they've had a single glazed outer unit with a double glazed inner unit, and you can open the two to get into the section. And the reason that they do that is to protect thermal shock on the second double glazed unit. So if you have an incredibly cold outer and a very warm inner, you get lots of shifting through the glass, and it causes the units to break down quicker. If you keep an existing single glazed or a poor performing double glazed unit and put a new double glazed unit inside, you get really good longevity to the second unit and much reduced carbon emissions. So this is a removable, pneumatically activated secondary double glazing unit, which can go inside listed frames without planning permission because it's not mechanically fixed. It has a seal that blows up around the outside. So just these are the kind of ideas we need, where we're not throwing out things, we are thinking about how we can upgrade and retrofit. Thing 3 is to design for a long life and flexibility. We can't knock things down, and we really shouldn't be tearing them all apart. So we need to think long-term and intelligently about how buildings can last for a long time. You know the stories. I mean, here's some great examples of where buildings have been adapted really intelligently. And I think this idea of adaptation and understanding your building will have a very long life is absolutely critical to the thinking. So, for example, I'm going to talk about a little office project we did. There, we imagined what the building would become after it was not an office any longer and it became a house. How can we put things in now to reduce damage and alteration at a later date? Thing 4, build for disassembly. I mean, this is an extraordinary building. This is in Bremen. It's their an extension to their town hall. And they realized that because of the way in which the political boundaries were going to change, they probably only needed a town hall extension for the next 20 years. And that became the kind of the driving mantra for the design of the building. So they they designed it so that it could all come apart and be reused. And in fact, they were so they used many reusable modules, common sizes of things so that they could then go on. And actually the builder, the contractor guaranteed 20% of the residual value at the end of the building life because of the way in which it was constructed. They reduced the amount of concrete and they made sure everything could come apart. So if you're going to do that, you need to remember where you put your stuff. So this is a very simple one about materials passports. which is starting, that was actually the first one was done on that previous project, where they listed and categorized where all the materials, what they were and where they've gone. And that is a really interesting challenge, but clearly something we need to tackle. So it's not just good to make it come apart, you need to then log where that goes. And critically, we need to build with less waste. There's some really interesting stats about that. I know this was about 10 years ago, maybe since the material costs have spiraled quite in the way they were, but there was an estimate that 10% of all materials that went to a building site left in a skip or unused. So that is a huge waste right there that we need to be tackling. So we need to be thinking more carefully about moduling of materials from the design phase right the way through. We need to build with less waste. So how do these things manifest? Well, we did a small project for the building I'm sat in now, which is our practice office, called Black Barn Studios. It was originally an equestrian building, a 1960s timber steel frame with an part asbestos, part concrete roof. And we got planning to convert that into our office, and we designed it so that we could reuse the structure, the floor slab, the concrete blocks, actually the timber from the horse boxes inside. All of these materials were taken apart carefully and reused. So we cut some simple minimal amounts of drainage into the floor. And as I said, we not only designed it for the current use of the building, we overlaid how this could be converted into a house going forward and cut in the drainage for those future uses and cap them as well. So minimal cut to the floor. We then adapted and strengthened the steel frame to take new corrugated iron and PV roof, and designed the building to sit inside the building. So rather than sort of smashing up the floor, we just put a very thin leveling screed down. So we were working on a flat area. And the great thing is, because we were building under a roof, we were really protected from the weather and the elements during construction. You can see what we used to screen the sides of the building was geotextile, which then became under the car park and the road when they went in. So they were used once and then repurposed for later in the building. We then had a timber I-beam, Styco I-beam frame, pre-engineered, pre-cut, pre-labeled and delivered to site, which meant that we massively reduced waste because they could do nesting of all of the cutting in the factory. So there was really minimal waste, and we did very careful ordering around the amounts of insulation. In fact, we got one bale of insulation left at the end of the whole construction. You can also see that we reused the concrete blocks from those walls to make a sort of tray, which we then put a radon membrane all inside. I don't know if this is going to work. I'm hoping it's going to work because it's a nice film, but I don't know how you make. Oh, there we go. So we then built this timber I-beam frame all onto insulation. We purposefully spread the foundations quite wide with very high compression insulation under the walls, so that it spread the load down onto the concrete slab, and we didn't have to in any way reinforce it. As you can see, the building is completely constructed inside the existing frame, which went up in, this is over 6 days, this erection. And we then boarded it out with a highly breathable external, internal, and blew it with fiber. The great thing is, because we had a really accurate 3D model, we could be really clear about all our wastage. We had hardly any wastage at the end of the project. And we made the building as simple inside as we possibly could, so that we could then move walls at a later date. There's only 5 columns. And crucially, we laid the floor in insulation, 2 layers of insulation. And again, designed that so that it was laid the insulation with as few cuts as possible. So when we come to lift the floor, we can reuse those insulation pieces. The floor was a caber deck floor with a UK made elm floor that we specifically found a UK supplier manufacturer floor for that. And then you can see building inside a building, waterproof and airtight. We then could take the skin off the building and paint it and redo it. Airtightness, we got to 0.03, so twice as good as passive requirements. And then you can see the frame and the PV going on. So this is the problem with a lot of Part Q, Class Q, and these kind of alterations, is that people try and put the insulation on the outside of the building, and therefore the steels basically are just not designed for it. So you end up rebuilding the entire structure. We've used about 5 cubic meters of concrete in the construction of the whole building, so it's incredibly low carbon from that perspective. We then use glass, old windows that came off a job that were going to end up in a skip that we stored for a year and then used, and all the wood on the underside is from the horse boxes that we plane down and reuse. The walls are Thermocell, so that's about 40% recycled, I think, on site. You can see the brilliant creative use of provision for hand wash facilities, and we used all the steel off the building to create a temporary store rather than getting a lockable port cabin shifted on and off the site. I'd rather pay labor than materials. So we built a little shed using all the raw materials during construction. There you can see the building. This is the lovely elm floors that were made in the UK by a guy called Sutton Timber. And you can see that, it's heated by an air source heat pump and through the MVHR system. And it is just off passive. It is 17 kilowatts per meter squared per annum. And we sort of realized that going to the next step to get to passive was such a significant input of labor that we decided that this was probably fine. And that's UK grown timber and all native planting. It sits in 3 acres where we're doing regenerative, it's all wild, rewilding and trying to bring back soil health from where it's being damaged by the horses. And you can just see the solar shade there over the back window, which is reused industrial walkways. So it's kind of very, and actually you can see the concrete step. There was some concrete retaining elements that we sliced up and used to make the step. So, and the concrete slab you can see in front of you, we've now cut up and cut flower beds into the floor slab there. So again, just trying to be really sensitive, use as much of the, work with the building, I think is the key thing, is you have to listen to the building in order to get, in order to really drive down the carbon. We're trying to do the carbon analysis on that. We didn't do analysis prior to construction, but we're trying to do we will do that eventually, but at the moment we're running through all of the orders and all the dockets that came to site to actually analyze the as-built carbon rather than using an LCA one-click model. We will then go back and redo an LCA one-click model to try and understand the gap between actual built carbon and projected built carbon, because I think there's probably a lot of learning there. And I wouldn't be surprised if, much like the performance gap in buildings, it's quite large, but we're trying to sort of delve into that a little bit. I've still got 4 minutes, I think, if I'm correct.
Yes, we're fine.
I'm just going to run through a very quick another way that we've looked at the carbon journey. So this is in our village where we are now. We're building an affordable Passivhaus community-led housing project, CLT, two housing blocks and a community sort of building. That's the north block, this is the south block, and this is the community building, which is actually slightly changed. We started this about 4 years ago, and we are hoping to start on site in about a week, I think it is. We signed the contract, actually find the final JCT on Monday. So the buildings themselves will be passive and energy positive. So they will export about 5,500 kilowatt hours per year. Just quickly, just to drop back onto this house, this building, sorry, the office exported 2.5 megawatts last year, including charging about 8,000 hours into cars. So it's carbon positive, it's energy positive as well. So understanding that it was energy positive in use, tick, for the kind of life cycle carbon thing. So then it was like, okay, where are we with the carbon, embodied carbon? So what we did is we ran a number of scenarios to analyze this. The first one was literally, if you built this using these standard materials, what is the carbon? We then said, okay, let's try and look at using local materials. What does that do to carbon? And then let's go to a third scenario where we're using as much recycled material as we can, as much local materials, reclaimed materials, and slightly changing some specifications. So for example, we were doing the modeling and the sanitary ware was coming up really high, and we dived into that and realized steel baths have an enormous carbon footprint compared to an acrylic bath. Now you would think, oh, well, a steel bath's going to last longer, but unless it's secondhand, no, it's much worse than acrylic. So we sort of really dived in without changing the design, but really specifying as close as we could from a cost perspective, but also from a carbon perspective. So where we started is a C rating, so that's 480 kilograms of CO2 emission per meter squared, and that's a total of about 628 tons. So that's doing no recycled and just standard delivery. And this is quite interesting. This shows you where that energy went. And the big one you'll see straight away there is the energy production systems, which is basically the PV. PVs use a hell of a lot of embodied energy, have a lot of embodied energy, but obviously they produce a lot. And increasingly the thought process around PV is unless you can replace an existing roof or replace a roof material with a PV, because of the speed of decarbonisation of the grid, it might not be the best thing to do. Unfortunately, the government are trying to get PVs to go everywhere, but that's not always the best answer. I think the subtlety to that carbon conversation around PV is my suspicion, and maybe this is a really interesting thing to hear from other people later, is my suspicion is that if you're charging electric cars locally or batteries locally off the PV, it probably knocks down the embodied energy sort of payback quite significantly because you don't have the losses over the grid. But that's the assumption I've made. It'd be really interesting to hear if anyone's got any thoughts on that. So then we did scenario 2, where we just looked at transport improvement. We've only got down to 622 tons. We've only taken like 6 tons or 7 tons out of it by thinking more about transport. Just to be clear, this is a fairly already a good building because it's engineered glue-lams and it's wood fiber and all that. So it was a good building to begin with. We then got to, this is still with the PV, we got down to 424 tons, up top end of a C, by looking at reclaimed slates, local material provision, reclaimed steels on the balconies, changing some specification. But in order to really get towards the REBA 2030 guide, there was quite a lot of foundation costs, carbon foundation costs, because of the ground and desiccation to do with some trees. If you take out the PV, we could get to a B, but then it's not energy positive. So it really, so this is just getting to the 2030 guides of below 300 kilograms per meter squared. And that was really hard. And this is a rural site. Yes, with some quite expensive foundations. Yes, 2 buildings. But don't be under any illusion. Meeting those 2030 targets is going to be one hell of a challenge. And I don't know where this office is. I suspect it's sub 200 kilograms per, I think probably quite a bit below that. I need to get that certified. But I suppose if there's one thing that comes out of this is like, you really need to start engaging in carbon modeling early. There's so much lessons to be learned, and it really isn't that straightforward. And it is going to massively change the way in which you design. And one of the key things to think about is how we can tap into the circular economy thinking, I think, to try and drive down the embodied energy, upstream embodied energy prior to coming to site. I'm going to stop now. I could carry on, but I think Anne-Marie is probably much more sensible and accurate about stuff. Thank you very much.
Cheers, Charlie.
Oh, absolutely. That was amazing. A really, really amazing example to look through. And I think hopefully we're top tailing the 2 presentations, because I'm going to pick up on many of Charlie's themes as well, and kind of the interpretation or the the challenges that we've had with very similar issues at a different scale to do with the circular economy, and how practically at scale on kind of big complex projects with complex supply chains, how that challenge becomes even more of a challenge. So yeah, just let me share my screen and we can get going. And I share your view as well, Charlie, about the embodied carbon of PVs. It's a really uncomfortable thing. People are very uncomfortable discussing that, but you can't get away from the fact that even the kind of the particular components that go into creating PV panels are kind of targeting particular habitats across the world, that there's exploitation of land use from the creation of them, like lithium batteries, the same kind of concept. So yeah, we kind of solve one thing, but we leave the problem of what we do with them on the other side. Okay, so Architype, we're around about 40 years now. We've been a sustainability practice for most of that time, very community led, community builds led practice, kind of the Walter Siegel method coming out of the 70s and 80s in particular. And probably we're looked at as kind of hippie, hairy architects by the kind of architecture profession until maybe 10, 15 years ago, when we really kind of started to focus in on this performance-based design around, natural materials, but also the performance gap that Charlie's mentioned in operational energy terms. And again, I think people are a bit nervous of Passivhaus and what that means and how that might limit their design, but it's one of those many constraints as an architect. We have to work in a constrained environment anyway, or as other members of the design team, and really it's an opportunity to create many different types of buildings with many typologies, with that primary focus on driving down operational demand and looking at how we can just, if we have to build new, how can we do it in the most efficient, demand reduced way? So I'm going to focus the process today a little bit on mostly on new build, but we also touch on retrofit and the whole life carbon aspects of that as well. Just another particular thing to note is that, you know, these buildings we can design and deliver and operate, but unless we actually understand how people use them and the behavior of energy use in those buildings, how those buildings might protect or buffer the occupant from those behavioral patterns as best they can, is something that we're always trying to do. So whether that's on our own projects or others, as we are part of a consultancy, basis, we're constantly learning. So as Charlie said, you know, there's not enough, you know, I don't think there's one person who knows everything about whole life carbon and embodied carbon, because there's so many discoveries happening on so many different levels just about how we understand and interpret information. So I suppose the bigger concept, without just looking at operation or without being focusing on kind of embodied, is that idea about regenerative design, trying to account for everything. And I suppose that was the theme of the hour. You know, how do we account for everything? Are we accounting for everything? And probably between what we are presenting today, we're still not accounting for so many things, but we're trying to make a really good attempt. And we have huge challenges to that, you know, never mind. And I totally agree, you know, we definitely have a performance gap in embodied carbon and whole life carbon terms for sure. And there's a huge misleading going on out there kind of in terms of policy within the government, that there's a kind of ignorance to the whole life carbon question, because we've now focused on the kind of trendy phrase net zero, which just refers to, you know, essentially glorified decarbonisation of the grid and nothing really to do with demand reduction. So we have that disconnect. And we have disconnects between life cycle costs and life cycle carbon. So as designers, we're starting to get a bit more literate in terms of life cycle, whole life carbon concepts and applying them to our buildings. But actually in terms of life cycle costs, the QS or estimating side of things, and also clients don't really fully understand or are literate enough in their own management of their assets to understand how life cycle costs can have an overall benefit if we look at life cycle carbon in the right way. We also have a terrible reputation as an industry of working in siloed approach to our designs and very kind of linear approach to, you know, the architect gets the design done, then the engineer comes along and puts some kind of services in there, and then the, you know, the structural engineer 6 weeks after the architects decided what their plan is, decides that he'll put the structure in, and it's very divorced and dislocated when it needs to be an integrated approach. And the other weakness is the ambiguity around the different modeling tools and kind of where those modeling tools information comes from. So I know we're all very aware of SAP and the weaknesses and strengths and limitations of SAP and other modeling softwares, but I think also we're going to find the same in terms of whole life carbon tools. And we'll have, you know, this idea that there's different tools being developed for different consultants. And I see it all the time now, a structural engineer presenting a whole life carbon model to a client without the whole finishes involved, without understanding the operational energy of that building, or the cost consultant looking at life cycle costs from, you know, the standard RICS information without really tailoring it in a bespoke way to the architect's design. And in theory, we could have all these models and come together in a really integrated way and develop a really powerful, accurate design model that tries to really predict what's going to happen in terms of whole life carbon results. And of course, the other thing to quickly mention is that as Charlie's example is really like beautifully shown, you know, you can make really early decisions that can ultimately affect cost and value. But as we try and move through a project and we make those decisions later and later, you know, we're creating more cost, more risk, more pricing risk for the contractor, especially in a D&D situation, and they ultimately become less effective. So, you know, that last 5% that costs nothing to do in REBA stage 1 or the feasibility phase to make a decision on, suddenly maybe costs something significant at the end and then gets left out of the project, and that's a real pity. So it's become kind of, you know, more business as usual over the last couple of years. We have scopes now that have been defined around how we target emissions. Public sector now requires whole life carbon analysis to be carried out, showing how strategies can be put in place to achieve them. It's all a little bit hollow because it's also theoretical, and a lot of it focuses on stage C, so end of life carbon targets, which of course there's no industry set up for at scale really, and we're relying on governments changing every 4 years over the next 60 years to develop those areas as part of important policy, which I'm a little bit skeptical about. And we finally have, kind of robust definitions of what scopes mean and what boundary conditions mean in terms of what we can tackle. So, again, when we're talking about the operational maintenance and use, the B stages, we're fairly familiar with what those outputs can be now as a kind of design industry. We have a 1 to 3, which can vary, a 4 and 5, which I think, Charlie's looking at in that forensic detail to say, right, okay, how much carbon does this material use? Instead of just going to a standardized database, can we actually look at this alongside the EPD performance? And then we have the end of life stage, which we need to be very transparent about how we report on that, and I'll come on to that later on. And of course, stage D, again, the industry is not quite set up, but we have some amazing examples like Heriot-Watt University have developed a product called K-Brick. Two very innovative people there, which is 90% recycled inert materials from a building site. Building sites, it can be actually the site you're about to build on. And that idea of bringing a kind of circular economy focus to the construction industry is happening in these lovely little initiative ways, but in terms of something at scale, we're really not there. So an example of how we've been through the journey on this at a bit of scale is our Passivhaus project. The first Passivhaus secondary school in the UK. It was finished in 2018, 2019 here, Harris Academy in Sutton in London. So it's part of an overall kind of health and wellbeing cancer master plan hub right beside the bedside development. So, there's kind of no pressure from next door in terms of trying to create a kind of very good example of a building trying to respond to the environment and on operational energy. We had a very complex site, so the form wasn't as simple. We talk in Passivhaus about trying to keep forms very elemental and simple, and there was that lovely simplicity in Charlie's barn. This site, very lawyered up neighbours, and the sloped nature of the site had its limitations. So we had a very clear brief that there was a requirement for low carbon from a whole life perspective, as well as Passivhaus. And from straight away from the get-go, there was material choices we had to make that compromise that somewhat because of the site and the kind of constraints of the site. However, we still tried to manage to create kind of quite an efficient form ratio to minimize that overall heat loss where we could. But you can see this kind of stepping back. There's wings. It's kind of like a winged block that in maybe another site with another beginning, we would have tried to rationalize more and create more simplicity for, and that's just some examples of the sections and elevations. And so typical Department of Education driven scheme with kind of classrooms and corridors. We're doing a lot of education projects now in Scotland where there's a very open pedagogy and quite openness about how we can consolidate multi-use rooms and multi-use learning spaces that ultimately help a project buildings become more multifunctional and consolidated as sustainable assets in the future, rather than always being consigned as, well, this is a school building forever. It could actually be something else baked in from the beginning. So because of the slope nature of the site, the building had been robustly tested early doors about the different construction appraisals with our in-house carbon tool, Ecolab, where we were able to look at the kind of cost, energy and the embodied carbon or whole life impacts of whether we went with CLT, concrete or a hybrid option. So even though unfortunately we had to have a lot more concrete in the building than we would like at the time, and maybe there's more innovative design decisions that you would make now rather than 7 years ago about all of that, but we looked at having 50% GGBS cement replacement, which obviously takes a bit longer to cure and has an impact on site and program. So contractor has to be on board on that. We went with mass CLT, which has a higher body carbon content than a lightweight timber frame, for example. But of course, in the insurance industry we have on large scale buildings now, CLT seems to be the safest only option we can go with in terms of compliance for fire, whilst we wait for the timber frame industry to kind of catch up with their certificates, etc. And then we've had an element of a kind of hybrid steel columns in there as well for the spanning of the hall in particular. So a wide range of different spaces were created. So even in the limited kind of typology of the building, which was very much a school, we tried to create a sense of future reflexibility to allow for different pedagogical learning or to allow for some adaptation of different education needs in the future. So an example was utilising the span benefit of CLT, allowing flexibility for class sizes or study group sizes as we went forward. And there's a minimal material palette, which I'll come back to in the next few slides. I'm sure every architect, we all passionate about like working with the landscape and looking at biophilic design, but we tried to embrace some of that as part of the design process as well by trying to retain as much of the landscape we could as possible around the site in terms of prelim temporary protection and kind of ensuring that existing mature landscaping was, you know, protected as best we could, but also adding kind of other landscape features. And there's other visuals of prioritizing certain views to the outside, and, you know, again, well established that link with nature and well-being. While some products are quite high embodied carbon, which we've accounted for, and I'll go into in more detail, we've tried to keep a lot of the finishes as raw as we possibly can. So instead of kind of layering on kind of partitions or other finishes on top of particular materials, where we could get a compliant design, as you all know, the challenge with CLT at the minute is that everyone wants to close it up, especially when we're looking at non-domestic buildings, which kind of defeats the purpose of having the CLT. We were able to expose a lot of the surface finishes in this and try and keep them as kind of as natural is the wrong word, but as kind of unfinished or as raw as possible where we could. This project also had a brief around designing for the circular economy. So that's kind of stage D, design for construction. And there was just interesting learnings out of this. So we had, you know, the CLT, which inherently itself could be reassembled and used elsewhere at any point over its life, and like steel frame can be kind of modified and reused in a different context. However, the design and bringing together of that CLT had quite a lot of deep, long screw detailing, that when you would have taken those panels apart in the future, so it's still possible, but the panels themselves where the screws have been in, the structural integrity would be compromised. So there'll be an element of having to accommodate some waste percentage on those panels in the future, in terms of a reality of reusing them again. So again, we're not really, we put these aspirations in briefs and we try and design with the right materials, but ultimately when it comes to fixing those materials and getting specialist subcontractors on board, we can sometimes lose the purity of that deconstruction or disassembly concept. And I think we need to be very mindful that we can set all these aspirational requirements at stage 3 or go through planning or even have something aspirational towards tender, but actually when it gets to design and contractor responsibility and who's going to be liable for putting fixings together on systems, we're still a little bit behind, and the industry hasn't really embraced other forms of fixings that might have allowed the full panel to be used. I suppose the important consideration here is that the majority of the CLT can be reused, but there will be a percentage of waste where those fixings across a lot bigger spans have had to kind of penetrate, you know, penetrate those layers to the effect that they won't be able to be reused again, unless they're just made that little bit smaller. So I suppose understanding the material you're working with and kind of bringing that lesson learned forward means we're trying to look at kind of smaller panels or maybe some other system to support a series of smaller panels so that those panels can just, like in Charlie's example about floors and finishes, you know, you can just pop out and reuse them rather than the fixings becoming a limitation. And, you know, we need fixings, but there's just quite a bit to think about that involves supply chain at a later stage that we need to be mindful of as designers. So the Resolve framework, we tried to benchmark the project against that as best we could. And you know, we're quite honest with ourselves. We didn't hit all of the targets on this with the building. Like we weren't able to fully optimize and keep kind of circularity on all materials, for example, but we made a really good effort at trying to hang on to those and defend those through the construction process. We brought in an element of other regenerative design elements in terms of specific promises by the supply chain. Now, I mean, I am skeptical when someone says they plant 3 trees for everyone that's cut down, and tree planting is only one part of the solution, but you know, there was an attempt to try and seek out some of those best intents and best endeavours from quite a large supply chain. And interestingly, recycled newspaper cellulose we were able to use in the Larson Truss across the whole building envelope. And we're still doing that on buildings, you know, under 18 metres, with a lot of technical submission and support to building warrant and insurers, because, you know, it is capable to, you know, it is possible to create a fire safe timber frame construction, you know, which insurers don't quite believe, unfortunately, but, you know, we are able to prove that. So it's been great that we've been able to hang on to some of those more natural insulation materials as well on this project. The wings themselves and the orientations have been responded to, whether it's been south, east or west. So there's quite a lot of glazing on the building because of the daylighting requirement for education, which we've been able to counterbalance a little bit with shading strategies. Also the kind of layering and sequencing of the building as well. There's a Larson Truss which is hung on the outside of that building, which allows the cellulose to sit in it. So again, you can see there's this kind of an element of the CLT that if you unpeels the building in 60 years' time, there's a lot of reuse potential in what's there by virtue of that kind of layered sequencing of the build-up. Obviously, there's going to be some loss, like I said, about kind of the larger span to CLT, unfortunately, but the intent is there that there's a reuse potential. Not to the same degree as obviously Charlie's example earlier, that he's been able to prove already, but you know, the intent is there if the industry can facilitate it. And I think it's Zero Waste Scotland that says, you know, in the future, the buildings of today are going to be the repositories of the building materials we need in the future, whether we like it or not, actually. So I imagine this world in 70 or 80 years' time where you know, there's no resources left. We're living in some kind of Armageddon. And if we need to build something, we're having to really peel things back from other buildings and be very inventful and resourceful with how we put them together. So there's been lots of analysis on the kind of shading. And again, the kind of shading that has been added, some of the timber is actually designed to be reusable as well, but also just protecting and the kind of daylighting requirements that matched the education requirements on the building, because ideally we would have glazed the building a little bit less. You know, again, as Charlie said, the highest carbon intensity part of new construction as well as existing is glass and glazing. And, you know, we're running out of sand globally in the world, and, you know, silicate and sand being really important constituents of glass. We need to be really precious with that. But again, designing a building that has a reuse potential and a kind of flexibility within its educational typology, hopefully ensuring this building's longevity, as well as the wider master plan for the cancer hub in Sutton and London, which has a really strong kind of sustainability and reuse focus. So this is just an example or two from the site. Again, the assembly, the labour time, the amount of energy being used on site whilst a building like this is being completed is much more reduced compared to kind of a wet trade approach to construction. So there's lots of kind of positive benefits there. Of course, doing whole life carbon and having standard values for that means that, like Charlie, you know, as part of some of the research we're starting to look at is a similar way. How can we quantify that to show the benefit of this, to show the value maybe of going with CLT over maybe another construction method, even though, you know, steel frame assembly is also quite quick, and understanding those metrics of what site costs and site energy use are. Here's just an example of just where we've been able to pull back the finishes. So we've allowed the CLT and glulam beams to be exposed with an element of acoustics, then managing that treatment in the space on the ceiling itself. And as well, I know the lights are on in this picture, but the side washing of the light coming into the space as well from the two side roof lights, again, not very common in a Sports Department of Education England school, but again, the benefit of the primary energy being reduced on the building if that area can be used even just a few hours a day in natural daylight. The strategy for air testing big buildings like this can be quite significant, especially on the contractor's part. Wilmot Dixon was the contractor on this building. And what we did was we advanced various elements of the supply chain to come and create a sample room where all the training happened, and we did some initial testing in that room to ensure that the robustness from an operational energy point of view can be achieved. And I think one fan did that building in terms of air testing, 10,500 meters squared a building, and we got an air tightness of I think 0.3 or 0.31 air changes. Contractor's first time, I think it might have been the tester's first time doing a Passivhaus test on a building and not just the building regs one. And we were really happy, but also not too surprised because CLT inherently is an airtight system, and we were able to achieve that quite easily. Again, another kind of example of maybe embodied carbon of services. So TM65 has come out over the last year. And I mean, again, we're all just trying to get our heads around what that means and how we even account embodied carbon in services. But I think another particular way we can do that with Passivhaus is by achieving radiant asymmetry in classrooms or spaces and ensuring surface temperatures are even. We don't have to put radiators under windows, and we don't actually have to put MVHR or ventilation over windows either. So we can start shortening distribution runs in buildings to be on that inner wall where all our main core services run. So again, it's not just architects trying to be efficient with design, it's working with M&E engineers to wonder, well, how many kilometers of duct or pipe or, you know, insulation impacts of those services can we save in big buildings by just being more efficient and by trusting that the building envelope is performing. So I think that's really important from an operational point of view. Again, the heating system, this is pre-decarbonisation, but there is a future connection to district heating planned in for the building. We have two boilers here heating this building, two 160 kilowatt boilers, One is in use, the other one's in reserve. And, again, it's kind of at about a third of its capacity from what the kind of monitoring is saying. So again, we're having to deal with, there's some hot water on this heating system as well as some instantaneous hot water through the design. So it is picking up some of that. But the heat demand, if you see a colleague visiting, standing beside one of the 400 by 400 mil radiators in the room as well on an inner wall with a much shorter distribution route, is really impactful when you're standing in a kind of 60 meter squared space. So that is a full classroom he's in. It's not just a a study room. That the space distribution becomes that small, that actually the next step is there actually another way we can heat those spaces without even putting in that wet system to heat those spaces in the first place. And again, I think that's where we're missing a trick with the decarbonisation. We're putting in huge heat pumps. The embodied carbon of all these new systems is significant. Putting in oversized radiators, creating all very long distribution runs, massive buffer vessels for hot water generation and design, and not really thinking of the embodied carbon impacts of those systems. So just briefly touching on the whole life carbon accounting from the project. We've touched on this already about the different stages: upfront carbon, embodied carbon, the end of life, which is the slightly controversial bit, and then obviously the bit that we haven't really managed to grapple fully as an industry is the kind of other boundary benefits of reuse and disassembly, etc. So come back to the operational energy, here's just some benchmarking for schools in terms of energy use intensity consumption. So we can see all the DEC percentiles, the LETI benchmark, the REBA 2030 benchmark, and the partially occupied data that we have from Harris Academy from 2020, which we're just getting these graphs updated now to reflect 2022 data, which is, I think, sitting at around 40 now, not 32, because we have almost full occupancy now. So our design value of 51 energy use intensity in 2020, COVID was there, and it was phasing in students, so it's not a full classroom, was 32. So the design is performing with no performance gap. In terms of the comparison between carbon of CLT and carbon of concrete, we had a 20% increase when we compared both options, and we blended both options, as you saw, from a kind of concrete and CLT perspective, which would have led to a little bit less of a difference between the two, but still a significant increase on the carbon itself. We've included end of life here. But I'll come on to this in the next slide, just about the kind of clarity we need to be careful of around the end of life emissions. But compared to a typical CIBSE benchmark school, we have an overall of 55% reduction in whole life carbon terms of that building. So we've used EPDs and kind of standardized benchmarking for many of those results. At the moment, at scale, not that it's not feasible, it's actually amazing practice to be able to do what Charlie's doing and kind of pick out literally the delivery dockets, find out where the material comes from exactly, not just assume bricks all come from Austria, and find out the true nature of some of the carbon transport impacts, on A4 and A5, so travel and site works. They are big energy guzzlers, and currently the data of how much energy those two can be is so variable that the benchmarks alone aren't usually good enough to work that out. So being very mindful of that, and also being very mindful of how we address or show biogenic storage or sequestration, as we will know it as well. So I know the RICS data are bringing out, RICS is bringing out some new data later on this year. I'm not fully au fait with it, but I know currently the RICS methodology for accounting for whole life carbon excludes biogenic in stages 1 to 5 of a building's stages A1 to 5. Unless we can include confidently the impacts of stage C, which is the end of life stage, and the timber originates from sustainable sources, which we know can be highly suspicious depending on where it comes from in the supply chain. LETI then says, so we have the RICS methodology, and then we have the LETI methodology saying that biogenic carbon over the life cycle of a building equates to 0, because the upfront emissions of timber is so much better than any other product, really, but it does release carbon when it's burnt or composted, and that's unfortunately the default we have to go to with timber, because we really don't know what's going to happen with any material at the end of its life. So when we make grand assumptions about what happens at end of life and we report including sequestration, it can be very misleading. We need to be very, very careful of that, because we don't, unless it's written into the covenant or a deed of a property that legally that next owner in 60 years has to reuse that timber, or downcycle it but reuse that timber as a different material, we have no guarantee that it won't just end up being burnt or composted. So what we try and do, and these 2 pages just show what we're benchmarking all of our projects, like many practices, if they haven't been done through the construction period already. And what we're doing is, if you just look at me flicking between these 2 graphs, is including and excluding the biogenic storage to see how we comply with both the REBA targets and the LETI standards here. And I have to absolutely agree with Charlie here as well. Like it is a real challenge unless you start including biogenic storage to achieve those results. And we just need to be very mindful of that. Just to wrap up, I've only 1 or 2 more slides. Whilst it's kind of easy, in inverted commas, to get whole life carbon of new builds, and you'll see that we have a retrofit there, the Cambridge Institute of Sustainability Leadership, which is a very, very low carbon impact. We actually need to be looking at things on a much wider basis. So at the moment, we're doing a study across Scotland. There's about 30 buildings now, not just 23, where we're looking at a variety of different intervention measures to deal with operational energy, as well as decarbon, about net zero estates, but also looking at the whole life carbon impacts on carbon outside of, including the embodied carbon that's being added to those buildings as part of the retrofit. And what's really compelling out of that, and this is kind of a anonymized intervention graph, is that any addition of embodied carbon of materials to a building, once we decarbonize the fuel source and reduce the energy demand of that building, has a significant overall whole life impact. So I know there's a bit of scaremongering out there about how much extra material do you need, and do we need to do that to existing buildings? But actually there's compelling evidence that the whole life carbon boundary can be treated really well and can respond really well to that deep retrofit approach. And just to focus on this last slide, so touching on what Charlie said, getting your tools right at the start, integrated with your design team in a collaborative way, trying to build as light as possible. So we could have just built in concrete with Harris Academy and just left it simple, but we tried to bring in and compromise for the fact we had to compensate for the fact we had to concrete. Early assessment, greater reduction potential, that's the same for operational energy on its own as well. And carbon hotspots. So, you know, in Charlie's example, it was the floor and leaving that down there. We know a lot of embodied carbon can go into existing foundations, to rip those up, to put in new ones, or to be building foundations. In the first place, are very carbon intensive. So how can we lighten that in terms of our impact on the carbon percentage there? And setting achievable targets. So that whole estate study we're doing, we're actually helping set a band of general targets they can go with. And I know LETI and there's other great work on retrofit targets being done as well. But what we're trying to do is set bespoke targets based on bespoke ranges of targets based on typologies that's feeding into the Scottish Net Zero building standard update later on this year for existing buildings, which is starting to encourage the beta edition of that one, which is encouraging kind of people to look at a cross estate view of carbon, whole life carbon, not just individual buildings. Okay, that's me. Sorry, I rammed on a little bit, and I wasn't actually as succinct as Charlie.
No, I wasn't very strict with my timekeeping there, but that was. I
heard you, and I was like, oh, I better hurry.
That was absolutely fantastic. Thank you. It's obviously been met very favourably from the comments and everything in the chat. Yeah, I was just sort of inspiring and frightening at the same time, really. I mean, the amount of, especially going back to initially to Charlie's work at the barn, and the fact, you know, I love the idea that it's part workplace and part manifesto, and whilst it only took 5-6 days to do the initial erection, I'm presuming there was quite a long time in the thinking there, but the minutiae that you went through to then recognize that it's still hard. And if it's hard, bearing in mind the work that you've done, then it is, and then when Anne-Marie then goes on to talk about the bigger projects, etc., it is scary how difficult this is going to be, but you've shown, you know, you provided an enormous amount of information there and inspiration in terms of how it can be done. So that, thank you very much indeed. I'm conscious of the time, Anne-Marie, for you might want to slope off, but I know there was a couple of questions going to probably asked by Natasha to Charlie. There's one, your windows, are they on the open market yet, the windows that you mentioned?
Yeah, we've got a couple of samples in, and we're looking to do a limited, not yet, but it's a work in progress, and as soon as it is, we will let you know through Instagram or whatever. But yeah, we're trialing it and we're taking our time, so we don't want to go out to market and then have failures. So we're working hard and we're looking for a limited release. In the next few months.
Yeah, cool. Well, yeah, they will be favourably received. And I don't know what both of your thoughts are on laying solid reclaimed timber floorboards over underfloor heating rather than engineered boards, which have higher embodied energy. That was another question there from Natasha.
It's quite difficult, isn't it? Yeah, Charlie, maybe you can answer that one. Are you on mute?
Well, it's funny because you speak to some people. I mean, if they're reclaimed, they should be fairly stable. And if your delta is very low, i.e., the operating temperature you run full heating, but if you've got a fairly leaky building and you're whacking the water through at 35, 40 degrees, I suspect it's a bad idea. But if you're putting the water through at like 26, 27, as we find you can in well-insulated buildings, I think it's probably fine. It's probably okay. But I don't want anyone coming back and saying I said it was okay and getting sued on that. So speak to your supplier. But this is the problem, right? Is that everyone covers their asses with specifications, and we end up like structural engineers. We have a systemic issue here where everyone is trying to ask cover, and the thing that suffers is budget and planet, basically. And at some point, we need to have a grown-up conversation about risk on all these things. So we're talking about fire risk. We're talking about, since Grenfell, everything's gone absolutely, really shifted. And that's not for bad reasons. There's some very good thinking about why those things have had to shift. And we know that there's been like poor action in the industry. But equally, I think there's a lot of bad decisions being made because of fear rather than knowledge. And that's incredible. We just don't have the carbon capacity to just do that, I don't think.
No, we are down a very damaging route with the timber frame and the kind of the bad press it's getting from a fire compliance point of view, when actually, steel frame and other types of buildings, in terms of their potential and in terms of the kind of requirements around fire rating those buildings as well, are quite onerous, and add actually quite a bit of cost on the contract, the contractor side that we don't see, interest paint, extra partitioning. But I think until the insurance industry feels more comfortable and there's more data to support that, especially natural materials as well. There's no test data for fire for much of that, or test data to show it in a particular build-up that it's sufficient in a full build-up that you can get a 2-hour fire rating on a cellulose timber frame wall. And we've had some data indicating you can, but it's about how big that test rig is. Is anything actually compliant with fire? When you start looking into the certification side of things, and you realize that stuff that's tested in rigs does not really reflect any real life conditions. Actually, short of building a mock-up of a building and burning it down to test it yourself, there is actually no evidence really to show that whatever you specify is going to be safe in any kind of build-up. And that is kind of dawning, I think, on the industry as we speak. And I know what Thistleton have done quite a bit of work around this, and Letty are looking at it, and a few other people. But yeah, it's a real challenge, regardless of what you're looking at, whether it's steel or timber frame. I absolutely agree.
Cool. I know we could probably go, well, I think you could both talk for a very long time on this subject, but we have reached the end of our session. So I very much appreciate you taking your time. I'm going to upload the chat and everything and the transcript to Meshwork, so everyone can see that there's been lots of links shared. So that was fantastic. So thanks for everyone's engagement and involvement. And I hope you enjoyed this one. We will be having a session on timber soon anyway. So perhaps you can come along to that one as well, Charlie. That would be fantastic to hear your thoughts on that. But no, thank you very much indeed, everyone. And we're going to have a break next week because of Future Build, and then we'll see you the week after. Cheers, guys. Thanks, Charlie.
Thank you very much, everyone. Bye. Bye-bye.